Hello, good afternoon. Hello, good afternoon, Anak. How are we doing today? Hello, can you hear me, Anak? Hello.
Hello.
Hello, fantastic. We've got sound, we've got life. Awesome. Good stuff. All right, so how are you keeping otherwise? This is a way of catching up. All's good and ready to rock and roll?
Yep.
Fantastic.
Yeah.
Good stuff. Good stuff. Excellent. Right. So thank you for relaying the topic because I wasn't sure whether you wanted to go through chemistry. How did you get on with the homework questions and the assignments I left you? Of course, I did give you the mark scheme to those problems. Did you ever go at, I'm not expecting you to have finished all of them, but
Yeah, I didn't finish them all. I did a few.
you did a few. And how did you get on with those?
I did all right. Yeah, I think I did good. I did good.
Excellent, excellent. We want to establish understanding there, so you have established some good understanding. Excellent. Right, so we are going to switch hats here and delve into some physics for today, as you requested, and we're going to be exploring pressure in fluids. But before we do that, I just want to make sure that we are firmly grounded on this idea of pressure. So if you were asked to describe pressure or say what pressure is, what would you say?
I would say it's a force in a
Yeah.
certain amount of area.
It's a force in a certain amount of air, and that's a very good start. Okay, so sometimes you would have expressed this using symbols as force over area. Now, strictly speaking, and I encourage my students to also write out formulas in words because these symbols take away some of the nuances that are very, very important. So at the moment, it just looks like force divided by area, but that is not how physics strictly defines area, okay? So if we express this in words, we say that pressure is equal to the force normal to a surface. Now, the normal here is not encapsulated. So to encapsulate that sometimes, you can put a little symbol like this to remind you that it has to be the force normal to a surface divided by the area of that surface. Which means that if I had a force, a certain force, acting at some angle to some surface, yeah, and let's just imagine that this surface, well, let's just say 10 newtons, and I'm drawing a 2D representation here. So let's just say that this surface is, well, I'm just going to put the area of this surface and say 1 meter square at an angle of 30 degrees. It would be incorrect to say that the pressure is 10 divided by 1, which is 10 pascals. It would be incorrect to do so. However, if that force was acting at 90 degrees to the surface, then here now, the pressure would be 10 divided by 1, which would be 10 pascals. So in this particular case, if we had to find the pressure, we would try and work out what part of this 10 Newton force is acting directly vertically or at 90 degrees to the surface. Now, that is something you may or may not have done. Do you recall learning about resolving of forces?
No, I don't.
That's fine. I'm not going to touch on that. We'll leave that for another day. But what I want you to fully appreciate is that when you talk about pressure, it is the perpendicular force to a surface divided by the area of that surface. Are we okay on that?
Yes.
Excellent. Good stuff. Units. What are the units? I suppose I've given you the answer to that one. Ready?
Pascals.
Pascals indeed. Yeah. So when you talk about 1 Pascal refers to 1 Pascal is a pressure, and sorry, I forgot my A there, and it's a capital P because it's named after a French scientist. So 1 Pascal is a force of 1 Newton acting over an area of 1 meter square. Key thing to note is that generally in physics, this force will be expressed in newtons. So if your force is in kilonewtons, meganewtons, you need to remove those prefixes and make sure that you go into newtons. This area here must be in meter square. So the alternative unit, as you can see for pressure, is the Newton per meter square. The units have to be compatible on the left-hand side as well as on the right-hand side. So here we've got Newton over meter square. We must also have Newton over meter square, and hence the definition for 1 Pascal involving a Newton and a meter square. So far, so good.
Yes.
Excellent. Now, here, key thing to note sometimes is that I suppose maybe the best way is to throw in a little bit of an example. So we're going to say a force force of 10 kilonewtons acts normally on an area of 10 millimeters square. What pressure does it exert? Have a go at this one.
A force of 10 kilograms. What should is there anything called kilopascals? So like when it's
Yeah,
in
absolutely. Very good question, that Anak. So with any of these units, we can have anything that goes in front of them. We can have nanopascals, yeah, which would be expressed as NPA. We can have micropascals, micro symbol PA. We can have megapascals with a big symbol MPA. We can have gigapascals. We can have kilopascals. So these are just prefixes to describe the order of magnitude of what you are dealing with. So they can all go to the front just as they do when we're dealing with newtons or any other unit. And that's the reason why it is important to know what each of these prefixes denote, because they can be thrown in front of any standard unit.
Okay. I got the answer. I think it's 1,000 kilopascals.
1,000 kilopascals, not quite. Another go?
Yeah, I'm trying. I keep on getting the same answer.
All right, so it might be me that has made an error here. Of course, these questions were just made on the hoof. I know that it's not an exam question exactly, but I just wanted to make sure that you understand the concept. So how do we go about doing something like this? Key thing to remember is, like with any physics problem that involves a calculation, we've got to think of what formula should apply, show working, and of course, finally the answer, your units, and sometimes you have to think about significant figures. So formula-wise, I'm sure you would have gone into your toolbox and use pressure equals the normal force divided by the area. So force is in kilonewtons, so we're going to have to diffuse this. So 10 kilonewtons, kilo means you have to multiply whatever that number is in front here by 1,000. So this here is 10,000 newtons, which is what's going to be applied here. Now the area we're told is in millimeters square, and we know we have to work with meters square. Now, if you're a bit puzzled as to what the conversion is to go from millimeters square to meters, draw a simple shape. Yeah, so 10 millimeters square means that the shape would have on one end 10 millimeters and on another end a millimeter. If you multiply the areas of these two, or rather the length of these two, you get 10 millimeters square. But we want it in meters square. So 10 millimeters, I'm going to have to do what? Divided by 1,000, which would be 0.001 meters. Is that right?
Yeah.
Yeah. No, sorry, 0.01.
0.01. Yeah.
Thank you. 1 divided by 1,000 would be 0.001 meters. Yeah? This can be thought of 1 times 10 to the minus 2. That is 1 times 10 to the minus 3. This here is 1 times 10 to the power of 4. And we can use our mathematical toolbox as the whole point of mathematics. It's there to aid ease with interpreting. So there we go, 1 times 10 to the minus 3 times 1 times 10 to the minus 2. This is a simple powers laws of indices problem. Minus 3 and minus 2 are going to add and going to give me minus 5. So the power of the final answer, there's a 1, there's a 1, there's a 1. So my answer will be 1 times 10 to the power of, well, there's a 4 there. So it's 4 minus 3 minus 2. Minus 5, making it a positive, plus 4, 9. So the answer is 1 times 10 to the 9 pascals, or I can express it, 10 to the power of 9 has a prefix, which is a big G for giga. So I can write this, my final answer, as 1 GPa. Did you follow that?
Yeah. I got everything. It was just the shape bit. Just where you put the rectangle and like the 1 millimeter and the 10 millimeter.
Yeah, or if you want to remember alternatively, we can of course use the conversion that 1 millimeter square is equivalent to 1 times 10 to the minus 6 meters square. If you can remember this, fair and good. But if you can't, draw a shape. Yeah.
Okay.
Super duper excellent. So now we've just been talking about this idea of pressure. It involves there being a force acting over an area. Therefore, if we look at fluids, the idea doesn't change. We're still looking at what force is acting over a given area. To break this down a little bit, we're going to firstly start analyzing in particular, let me put another page here, liquids after current. Because fluids, of course, is collective for liquids and gases, but we will break the problem down a little bit into some modular pieces, and we're going to look at pressure in liquids. Now, just as a general overview, if I let's just draw some container here. And we've got a liquid. Where do you think the greatest pressure due to the liquid? Yeah, the greatest pressure due to the liquid. Where do you think that the greatest will be experienced? At point why or point X? Sorry, or point X, and why?
Point X.
Point X, correct. Why does point X have the greater pressure?
Is it because there's more like water above it, so it would have more force?
You're absolutely right. So even though, even if we kept the area constant, you're absolutely right. There's a greater weight or greater column of liquid above X, and that is what's creating the force that is acting over a certain area. You're absolutely spot on. And the reason why the weight arises is as a consequence of the pull of the earth on the water particles, because they are particles, they're experiencing the gravitational pull, therefore they have weight. You're absolutely right. And if I drew a cross section here, like so, we can visibly see that the liquid above Y is given by that highlighted portion, but the liquid above X is inclusive of that highlighted portion and this extra portion on top. So you are absolutely right. So we say that pressure in a liquid arises due to the weight. Pressure in a liquid arises due to the weight of a given column of liquid above the surface. Above, I'll say a given surface, above a given surface. And I'm referring to these here as the surfaces. We can still visualize them as a surface. Okay, so the key idea to note is that in a liquid, the pressure is at any given level, at any given depth. Let's call this depth D. At this depth D, the pressure or the liquid pressure will be acting in all directions. And I'll state that here. It's important to appreciate that nuance, that liquid pressure acts in all directions. Now, have you learned about vectors and scalars?
Vectors have magnitude and direction, and
Good.
scalars only have magnitude.
Good. So what do you reckon pressure is? Is it a scalar or is it a vector?
It's a vector.
It's a vector? So
Yeah,
can you tell me, if it's acting in all directions, can you tell me which direction the pressure is acting in here? If liquid pressure acts in all directions, what direction would you use?
I don't know.
Okay.
Would it just be a scalar then? Because if it's using in all directions, it knows like specific direction.
Yeah, well, it is actually neither. It is neither a scalar nor a vector. I will not confuse you because now we're delving into the dimensions of very advanced physics, but I'll just give you a bit of an idea so you can understand why it is neither, just to give you an appreciation. Imagine we have some kind of rubbery cube like so, okay? And there it is resting on the ground on its vertex. And you direct, you direct a force at the top. What's going to happen to this rubbery cube now? It's going to squash, isn't it? It's going to squash like so. So now you're exerting a pressure on it. So some of it has shrunk and some of it has become longer in the directions I'm pointing here. So in which direction is the pressure acting? Is it acting downwards? Is it acting sideways? So this here is actually what you call, it's got a certain, it's its own family. It's known as a tensor. Pressure is a tensor, but don't worry. This is just for extra knowledge purposes. So just to know that it is neither a vector nor a scalar. So if ever you're asked to give examples of vectors or scalars, please do not include pressure. That's the reason why I wanted to talk about this one quickly. So far, so good.
Yeah.
Excellent. So we know we have established here, you have the understanding that pressure increases with depth.
Yes.
In other words, we can say that pressure is directly proportional to the depth of, or H. I'm going to call this the depth. It's directly proportional. Now, have you learned proportions in maths?
In physics we have, but that was in year 7, but I still get it.
Good. So we say that as you increase the height or the depth, the pressure increases. You make this smaller, this also gets smaller. So that's the relationship there. Excellent. Now, let's also think about what other things are going to affect the pressure. How do you think the pressure would change now if I say used a liquid of a greater or higher density than another liquid? In which liquid would you expect a higher pressure to be experienced? In the higher density liquid or the lower density liquid?
Could you repeat that?
So I'll draw a diagram here. So imagine we have two liquids, same depth.
Yeah.
Now I tell you that the density of this liquid is 1,000 kilograms per meter cubed, which is the standard density of water. And I tell you that I've got another liquid here where the density of it is 2,000 kilograms per meter cubed. How does the pressure at the bottoms of these two vessels compare? In other words, in which of these vessels will there be a higher or greater pressure at the bottom, A or B?
B.
Correct. And why is that?
Because it has a higher density, meaning I don't
There are
really
more
know what it
particles in a
means,
given volume.
but yeah.
Correct. There are more particles in a given volume. So if I take a column of liquid, as so, there will be less particles in this given volume compared to the volume for B. So there'll be a greater weight, there'll be a greater force. You're absolutely right. So pressure also depends or is directly proportional to the density. Increase the density, increase the pressure. But we also know that it's directly proportional to, well, I say it's directly proportional to, but these are the main things that is directly proportional to: the density and the height, which we looked at here before. But of course, we know that what is creating this force? Well, it's the weight is created due to the gravitational force of attraction. And what does the gravitational force of attraction depend on? Well, it depends on which planet. So we can also say that pressure is directly proportional to the gravitational force of attraction. If the gravitational force of attraction is bigger, then the weight of the force that's acting on a particular area will also be bigger. Do you agree with that?
Yeah, just one question. Gravitational force of attraction, is it the same thing as gravitational field strength?
Correct, absolutely. So the other names, so gravitational field of attraction has lots of names. So let's just spell them out. Gravitational field strength is the same as acceleration due to gravity. And sometimes it's just gravity. And any other gravitational field strength, acceleration due to gravity, and also you may hear this very rarely, acceleration of free fall. Very, very rarely. They all mean the same thing. And on Earth, this is all equal to 9.8 meters per second square, or sometimes expressed in newtons per kilograms. They are the same thing. Are we okay with that?
Yeah.
Good. Alternatively, if you want to see where it is all coming from mathematically, I've given you a very intuitive feel for how things are related, blank page after current. So we can join all these relationships and therefore say that pressure is given by rho GH. But I have done a shortcut here. I've tried to give you an intuitive feel for how pressure in a, so this is the pressure due to a column of liquid only. Better put that word only, and we will see later on why I've put that word only. If you want to see where everything links in mathematically, and I'm sure you will, because obviously you're a very able student, so it might help just to get a better understanding. So we say that the fundamental starting position is pressure is the normal force divided by the area over which that force acts. So let's just look at a scenario where if I had a column of liquid, and I'm just going to, right, I'm going to try and say, here we go, draw a 2D representation as best as I can. See if we can, yeah, let's try to do it this way. So this is my column of liquid. I'm taking a column of liquid. Here we go. And I want to find the pressure acting over a certain area at the bottom of my container. So we want to work out what is the pressure. So what's the first thing I got to do? Well, let's imagine that this here has a length L and it has a side W and it has a height H. Well, then the area of this surface, if I'm using P equals to force divided by area, well, the area is length times width. Following?
Yeah.
Now, what is the force? Well, the force is due to the weight of the entire liquid that's above this area. Now, what is the weight of that? Well, weight, the formula for weight is that weight is mass times gravity. Well, I need to know what the mass is then, because G doesn't change. But I need to know what is the mass of this column. How can I find out the mass? Well, if I'm told that the density of this liquid is rho, which is the Greek symbol we use for density in physics, please, it's not a P, it's a rho, then I can use the formula that density is mass divided by volume. And to find the mass of this column, well, the mass of that column will be given by density times volume. Are you following so far?
Yes.
Good. And what is the volume of this column? The volume of this column is length times width times height. So the mass of this column is the density of the liquid multiplied by the length times the width times the height, which is what I'm going to put here. So here now, I'm going to have density times length. Let's take this off. By the way, we've still got this G symbol here. We're going to put it at the end. So length times width times H times G. What do we notice? The L and the W, these cancel off. So my final formula is rho GH.
Yeah, but aren't the length and the width different in each equation?
No, the length here of this column is still L,
Yeah,
but it's still W.
you're trying to find the density of like. Oh no. Oh, okay, I get it. Sorry.
You okay?
Yeah, I get it now.
No problem. So this is where this formula originates from. I try to give you an intuitive feel, but here I've also given you a mathematical approach to seeing that we started off with pressure equals force times area to get to that formula. So if I have two, it doesn't matter what shape I could have. I could have used a circular shape. The formula would have still been the same. What this means here is that It doesn't really matter what the shape of the container is, as long as the heights are the same and the densities are the same in two liquids. The pressure at the bottom will be the same, because pressure only depends on what is the density. If the density is the same, G is the same, they're both on Earth, and what is the height. If these three things are the same, it doesn't matter on the shape of the container, the pressure at a given depth, for if the two given depths are the same or it could be more, will be the same. Does that make sense?
Yeah.
Good. Right, so that is liquid pressure. If we look at atmospheric pressure now, oops, let's go back to this side. If we now analyze atmospheric pressure, this occurs is due to molecules, and specifically air molecules, colliding with a surface. That's what causes atmospheric pressure. Now, of course, the Earth is surrounded by an atmosphere. And it'd be very easy to think, well, why don't we use P equals to rho GH to calculate? So the atmosphere itself is very thin. So let's just say this here is our atmosphere. The reason why we can't use this formula to calculate for a given height, the pressure, is because the density changes. So we have less particles at the top than we do at the bottom. Greater density at the bottom. And remember, likewise, the pressure is still to some degrees related to the weight of the air above a given surface. By the way, this is Earth. Let's make sure we make this very clear. Okay. So because the density of the air, so with increasing altitude, I'll just make a note here, with increasing altitude, density of air decreases, and so does the pressure. Okay, because the pressure is due to the molecules colliding with the surface. If we have got less molecules, there's less collisions with the surface and therefore less pressure. So if you plotted this as a little bit of a graph where you had pressure versus altitude, this would look something like this. So at higher altitudes, your pressure is decreasing. So remember here when I said, just to now give you a little bit of detail, why I now said pressure due to the column of liquid only. Why did I say only? Because there will be air particles above this column as well. So if I want to work out the overall pressure, I need to add up the pressure due to the atmosphere, which will be pushing down, and the pressure due to the column. So here I did not want to confuse the calculation, so I ignored the air pressure. Can you see why I now included the word only?
Yeah.
Good. So overall, when you're using a pressure gauge, the pressure gauge, if you put a pressure gauge at the bottom of a river, it will be measuring both the pressure due to the liquid and atmospheric pressure. If you want to find the pressure due to the liquid alone, you need to subtract away atmospheric pressure, which has a value of about 101 kilopascals. So it is pretty intense atmospheric pressure. And just to see if you've ever tried this little demonstration, it's a nice little experiment to try out. After take a piece of newspaper, and open it out to its full width and length and place a ruler. So let's imagine now you've got a table. Oops. And you place a ruler. And some of it will be encased on the paper. And give your ruler a sharp karate chop, if you like, downwards at the edge of the bench. And what you notice oftentimes, if it's a wooden ruler, you're going to end up breaking it. Now, what most people think, they think it's going to fly off because you've hit it on the edge and it's going to fly off. Why doesn't it fly off? Well, there's atmospheric pressure pushing down on this, and there's a lot of it. So if there's 101 kilopascals, and this area is 1 meter square, now pressure is force over area. It means the force acting due to the atmosphere on this paper will be equal to pressure times area. 101 kilopascal is 101,000 pascals multiplied by an area of 1. It means that on that paper, you have 101,000 newtons acting, pushing down. Now, 101,000 newtons is equivalent to 101,000 apples resting on that paper. So atmospheric pressure is real, and you can do some really funky, cool things with it. Right, any questions?
Would the ruler be under the paper or above it?
Oh, sorry, you place the ruler inside the paper. So the paper is above the ruler, yeah?
Okay.
And I will, because whilst we're at it, why not? We've got technology. We might as well bring this to life. So if we go to we'll watch a quick demo and then we're going to get into some exam questions.
Okay.
Right. I can find it. I'm not sure what I'll put in YouTube. I'm sorry. So look at this. Maybe that one. All right, here we go. Let's go to this one. I wasn't even sure whether I could find these things on YouTube, but believe you me, the people who make these videos of these things, which is good. Share sound. Skip ads as always.
Hi, I'm Jared, back for another experiment with air pressure. Lesson 3. This one is full of action. It involves needing a newspaper and rulers. One caution, some of the rulers you get, you have a metal strip in them. You want to stay away from the metal strip because that could cause some problems later. So just a very simple wooden ruler. No plastic, wooden works the best. And what I want to do, again, is just emphasize that air has pressure. So I'm going to need a sheet of newspaper, not the whole thing. You want the sheet that opens up into a full spread. So I have my full spread, and I'm going to place it with the fold facing up. What is pushing down on that newspaper? Air. All the air in this room is pushing down on top of this newspaper. So can air be strong enough to break this ruler? Well, if I hit this ruler without the newspaper on top, there is some air pushing down, but not a lot. It's not going to counteract my force of hitting down. There's some air pushing down here. I push down here, the ruler's going to flip. So how can I increase the amount of air pushing down? Well, I give a greater surface. So using this paper, now I increase my surface area. The air pushing down, you can see I have all this surface area for the air to push down on. I'm going to smooth it out. I'm going to slide the ruler under. Now, when I strike the ruler, all this air pressure is pushing back against my hit. Is air strong enough to break the ruler? We're going to find out. Here we go. On the count of 3, I'm going to hit hard and forcefully because I want to create a seal around the edges of the newspaper. If I hit too slowly, air is going to be able to get under that newspaper and it will not work. So fast, hard. 1, 2. Whoa. You can see, ruler broken, newspaper.
Okay, right. So that is what I was referring to. Does that make sense now?
Yes.
Excellent. Now, the next thing I also want to just touch on very quickly is that you may get questions to maybe describe how a plunger also works. Again, they're relying on the principle of air pressure. So if I have a plunger placed against or pressed against a smooth surface, and I don't do anything, well, the air pressure is the same on both sides. So if you like, the force that this is exerting is the same as the force that the particles inside are exerting. So this will just drop. But when I push it inwards, what does it do? It expels a lot of the air. And remember that the pressure is caused due to collision of the molecules with the surface. Okay, pressure due to collisions with, I'll put it in bold, with surface, not with each other, with the surface. Okay, so now when I push the plunger in, what does it do? It expels the air or the air molecules. Now they're less, well, flattens out. There are less molecules colliding with the walls because I've expelled them, and there are more air molecules colliding with the surface. So there's a greater pressure on the outside. In other words, a greater force. So this sticks to whatever it is that I'm trying to stick it onto. Any questions?
Is it because like the area or the volume decreases, so there'll be more collisions?
Oh yeah, I see what you're saying. The area itself, you're right. They'll be because this you're flattened, so there's an increase in surface area, but also there's less particles in here. Because I don't know if you've ever used one of those plunger things that goes, I don't know, tom-tom or something onto your window, and you press it. You always expel air out.
Oh, okay.
It is the expulsion of that air, meaning there are less particles colliding with the surface. Because remember, the examiner will be looking to ask you to see if you can remember that atmospheric pressure is due to collisions with the surface. The less molecules there are, gas molecules, the less collisions with a surface and the less pressure. And that is why air pressure decreases as we go up, because the collisions of the molecules become less. There are less molecules at high altitude. Are we following?
Yes.
Good. Right. Some questions. Here we go.
Significant. Is it C for question 1?
Correct. Now, there's also an additional consequence to this. Ever heard of the bends?
No.
Right. The bends is what divers experience. If they dive way too deep, what happens is that there's a lot of nitrogen in the sea itself. The nitrogen ends up going into their blood. And if they come up to the surface very quickly, it forms bubbles in their blood. Now, can you understand the consequences of having bubbles in one's blood?
Would it make the blood explode?
Even worse than that, because your internal system is a sealed system. It's not meant to have any air bubbles whatsoever. And essentially what that leads to is paralysis. And I've had family members who were deep sea divers, and essentially they have been paralyzed for life. Your organs stop working. At the worst, you die very shortly after. But if you do survive, you can't perform things as you used to, and it's quite a debilitating illness. So this is why when divers are coming up from a very deep waters, they have to come up slowly, and also obviously try and counter the nitrogen going into their blood. Okay, it's a very serious problem. So should you ever go diving at any stage in time, please be aware that pressure is something, especially liquid pressure, is something to be to treat with caution. Right, number 2, very good, absolutely correct.
Diagram show these. Would it be D?
Spot on. Spot
Would be A?
Not quite. Brings us back to the point. Yeah. In a liquid, pressure due to a liquid only depends on 3 things: the density, the gravitational field strength, and the depth. Is density the same? Yes.
Yes.
Is G the same? Yes.
Yes.
Is the height the same?
Yes.
Correct. So what should the pressures be at the bottom?
Yeah, but then there's more weight above A because it has more volume in it.
No. Pressure in a liquid does not depend on the volume. And that's the beauty of mathematics. It tells us exactly what the pressure will depend on. It does not depend on what's on the sides, as the maths showed us, and we could have used any shape. We used the rectangular cross-section. We could have used a circular cross-section. The maths would still have boiled down to this, believe you me. So it does not depend on the shape. It only depends on the height. And I know it's very difficult to appreciate it intuitively. And that is, well, happens in physics, of course, that some of the things that formulas come up with don't seem to agree with what we intuitively feel. But believe you me, the pressure will be the same at the bottom, regardless of the volumes. The maths itself doesn't tell us a lie. It tells us that the pressure will only depend on the height and the density and gravity. Very tricky question. So the answer for that one is D. Number 4.
Would be C.
Well done. Well done. Good. So, of course, you had your table. There's a weight of 50 newtons. And here you've got 3 Newton meter over that. Force is pressure times area. So the rain is exerting a force of 3 times 2, which is 6 newtons. So the total force here, you're right, is 56 newtons. Now, of course, they would also be very clever if they wanted to. They would say how much force is exerted on each leg of the table. Assuming the table has 4 legs, you'd have to divide that by 4. All right. Okay, super. Last one on the multiple choice. I'll be with you in 30 seconds. Just one moment. Just need to go and attend to the door. So just know.
Liquid X at top.
Hi, Anna, come back.
Hello. Yeah. When it says 9p, does it mean 9 pascals?
It just means 9 times some value of a pressure. So 9 times the pressure. But it's okay for you to see this as pascals, because if you see it as pascals, it will make the understanding of the problem a little bit easier. So let's go for seeing it as pascals. It's not going to make a difference to our approach, but it will just make it easier. Should we see it as pascals? Yeah.
Yeah.
Cool.
What does the H stand for in the question? Is it height?
Correct, that's the depth. So I know we call it height. Height normally you normally associate with something that's being measured from the ground up, isn't it? But in
Yeah.
this case, height simply just denotes the depth from the surface. Yeah, so in this case, height is measured from the top. That is where we measure the height from. In other words, H is equal to depth. Depth is always measured from the top of the water. And that's the same depth we use in the formula rho GH. It's the depth from the surface.
How in like the answer is there also depth in like when you're trying to work out depth, there's also depth in the answer.
Correct. Okay. So this really is very much a grade 9 type of question here. They've said here, let's just try and, with a physics problem like this, it's always sometimes helpful to just set up a little diagram so that you can see what's going on. And then it's easier to work with it from there. So we have two liquids, and I'll just put some containers. One of them is called liquid X, and the other is Y. Now let's assume that Y has a density, which I'm going to call density of Y. We're told that the density of this here is half the density of Y. So in other words, its density of this is half of the density of Y. That's the density of that liquid. In other words, that is equal to the density of X, of liquid X. It's half the density of Y. So you set up this mathematical problem using equations. Now we're told that at a depth H, so when this has a depth H, the pressure exerted at the bottom here, we decided to call it 4 pascals. Now we know that pressure due to a liquid is density multiplied by gravitational field strength multiplied by H. We are told that the pressure is 4, so I can start plugging things in. 4 equals the density, I'm going to express it in terms of the density of Y. Density of Y divided by 2 multiplied by G and multiplied by H. I've set up a formula or an equation for this scenario here. Following so far?
Yeah.
In the second situation, what do we want? We want a pressure of 9 pascals. So if I use the same situation, the pressure is 9. The density is the density of Y multiplied by G, but they're saying, what should the value of that depth be? That depth here, I don't know, but I'm just going to call it, let's call it X. I don't know what it is. So now let's just think here. If I simplify this mathematically, do you agree that I can multiply by 2 on both sides of the equation?
Yeah.
I'm going to get rid of this 2 here. That's why I'm multiplying by 2. So now I get an expression that says 8 is equal to rho Y times G times H. Are we following so far?
Yeah.
So can you see that this value here, rho y times g, if I use my first equation here, I have an expression for rho y times g. Well, this tells me that rho, or density of y, multiplied by g is the same as 8 over h. Can you see that I've used this expression here? So I've divided by h on both sides. Following that?
Yeah.
Very good. So in my second equation, which I'm going to label equation 2, by the way, this is equation 1. In my second equation, where there's a density of y times g, I can replace that with 8 over h. Because I found it from the first equation that that's what this amounts to. Remember, x is the depth we want to find. Are you following so far?
Yeah.
So the equation now becomes 9 equals to 8 over h times x. Therefore, what is x? So I times both sides by h over 8, inverse. That now crosses out, this 8 cancels out with the 8 at the bottom, that h cancels out with the h at the top. So the depth which we want to find, x, is equal to 9h over 8. So in other words, here, that height will be 9h over 8. And that will give me a pressure at the bottom, which will be equal to 9 pascals.
Yeah. That's
Very difficult, but I hope you may go back to the question maybe in, I don't know, 2 weeks time or 3 weeks time and see if you can do it by yourself. Just to
okay.
see if you've really fully understood it. So give yourself some time. Of course, you can go through it after the lesson, but give yourself a bit of time and then try and revisit it to see if you can work your way to the answer. But as long as you followed it, that's what's important. What's now remaining here are all long structured questions. Let me delete this because we don't need this page. Okay, what is now remaining are all actual exam questions, AQA exam questions, and they are all long structured. So I'd like you to have a go at these long structured questions. And then of course, yeah, so the test atmospheric pressure as well. So I'd like you to have a go at these. The mark scheme is included as well, so that you can then obviously mark to see how well you've understood the stuff. Do you have any pressing questions, or is that okay for you?
That's okay.
Superb. Righty, in which case, we'll call it a day for today. And well done today. There were some pretty challenging concepts, but you tried your best, and that's what's most important. So in the meantime, I will prepare the video on the board work, and I'll send that through to you. And I shall look forward to seeing you at some stage soon.
Okay.
Awesome. Have a nice day, and well done today again.
Thank you.
You're
Have a
welcome.
nice day.
Cheers. Bye, Nak. Bye now.